So for number 13, we are taking these curves, sine x and cosine x, and we're taking the area between them from 0 to pi over 4 and revolving about the line y is equal to -1. So I've drawn these curves, and it tells us that it's between 0 to pi over 4. So pi over 4 is here where they intersect, and therefore the area between them in this interval is this area over here. So in this area over here, we have to take this and then revolve it about the line y is equal to -1. So when we revolve it, what is happening is we're going to have these discs that have this width. They have the width of the height of cosine minus the height of sine, and we're going to revolve them about here, like so. That is a terrible drawing, but hopefully it'll make sense. Yeah. So these are our discs, and each disc is going to have an area. So when we sum up all these areas from 0 to pi over 4, it's going to give us a volume, right? Because a bunch of areas stacked up gives us volume. So we do know the bounds of our integral. It's from 0 to pi over 4. Now we just have to calculate how to express this disk, because this disk is constantly changing, right? Because the area between them gets smaller and smaller as we go from 0 to pi over 4. So because it changes as a function of x, so does the volume. So when we're going to set this up, this ring here is basically A1, so the bigger one, where we have, let's see, we're going to call this the bigger radius R1, and then the smaller one over here, this is R2. So this ring is basically A1, the area of the bigger circle, minus A2. So A1, we're going to have, we are going to go, the radius goes from here all the way, maybe I'm going to do this in a different color, yeah. So for A1, the biggest one, the radius starts here because that's the center at y is equal to -1, and then it goes all the way out to the upper function, which is cosine x. So the length of this radius isn't just the height of cosine x, right, which would go from 0 to cosine x. It goes from 0 to cosine x plus this whole distance of 1 that we had to get before we could get to the x-axis. So actually the radius, the size of it is 1 plus the height cosine x, plus cosine x, and then it's pi r squared, so we're going to square that. And I'm just going to expand this, which is pi times, and I'll FOIL it out, so that is cosine squared x plus 2 cosine x, and then plus 1. And now we have A2, which is once more pi r squared, but now our radius, and I'll choose a different color too. Now our radius here, it goes from the center, but instead of going all the way up to cosine, it goes to the smallest part of our area. It goes to this blue curve, which is sine x. As we can see, our width, it goes from the biggest radius minus the smallest radius. So the smallest radius, we have to go 1 until we get to the x-axis, and then we go the height of sine. So this length is 1 plus sine x squared, and that gives us pi times, we're going to FOIL this, so sine squared of x plus 2 sine x plus 1. Okay. So once we have this, our integral is basically a1 minus a2 to get this ring here. So we're going to go a1 minus a2 is equal to, I'm going to leave the pi outside once more, and that is, let's see, cosine squared x plus 2 cosine x, and then plus 1 minus sine squared x, and then minus 2 sine x, and then minus 1. So when we simplify it, this plus 1 and minus 1, they cancel out. And we have here cosine squared x minus sine squared x. Now, if we remember from our double angle identities, we have that cosine squared x minus sine squared x. This is equal to cosine of 2x. And the reason that we're changing this is because when we go to integrate this, cosine of 2x is very easy to integrate. We know that, whereas cosine squared x is not easy at all. So we thankfully we can substitute this for an easy double angle identity, and therefore our integral will be much easier to calculate. So once we have this, we are ready to set up our integral. It is the integral. It tells us from 0 to pi over 4. So from 0 to pi over 4. We're going to put the pi outside because it's a constant, pi. And inside the integral, we have cosine squared x minus sine squared x. So we're going to substitute that for cosine of 2x. And then once we've taken care of this, now we have plus 2 cosine x. So plus 2 cosine x, and then minus 2 sine x, and then minus 2 sine x, and all of this times dx. So these integrals from here, they're fairly straightforward. So that is just pi times the integral of cosine of 2x. This is a simple chain rule. This is just sine of 2x divided by 2, and then plus 2 cosine x. So that integral is plus 2 sine x. And then here, it's minus 2 times the integral of sine x. So the integral of sine is minus cosine. So minus cosine times minus 2 is plus 2 cosine. So plus 2 cosine x. And all of this evaluated from 0 to pi over 4. So when we plug in our boundaries, we're going to have pi times, let's see, sine of 2 times pi over 4 is sine of pi over 2, which is 1, and then divided by 2, that is going to give us 1/2. And then 2 times sine of pi over 4, so plus 2 times root 2 over 2, plus 2 times cosine of pi over 4, which is also plus 2 root 2 over 2. And then we plug in the lower boundaries, right? So minus sine of 0 is just 0, plus minus 2 sine of 0, which is just 0. And then cosine of 0 is 1. So minus 2 times 1, minus 2. And when we simplify this out, which is equal to pi, minus 2 plus 1/2 is negative 3 over 2. And then plus, let's see, these cancel out, plus that is 2 square root of 2. 2 root 2. And this is our answer for our volume.